Good morning, everyone. Happy Friday. We are talking about what do we do? We talked about how to take our gain root locus rules and manipulate them to do root locus for non-gain parameters. And then we ran through some options of when it's your job to decide what kind of controller to use, what are your options, and how should you decide between them. The main driver behind all of that was what are the requirements, and then what do the different controller options that you have, how will they affect the root locus diagram. And kind of the culmination of that analysis was basically if you've got lots of poles in your plant, it's often a good idea to introduce a few zeros in your controller. If you also need to increase the type number, then you want to put an integrator in your controller. And what I've just described, a few zeros and an integrator, is a PID controller. And so that led us to this discussion of you can either think of a PID controller as the weighted sum of three branches, the P, the I, and the D branch. And those operations, proportional, integral, and derivative, all act on the error in the system, which again is the reference input minus the output. Or you can think of a PID controller as, again, a 2-0-1 integrator subsystem. Those are equivalent views of the same thing. So to give you a little bit more, not just pure S-plane intuition about what the PID controller is doing, we looked at this picture, which was take the input, take the output without any kind of control, and just visualize what the error signal looks like in the time domain. Visualize what the integral of the error signal looks like in the time domain, and visualize what the derivative of the error signal would look like in the time domain. So here the intuition was currently the error signal gives you the present error in the system, i.e. if you only cared about now, what should your controller be doing? The integral of the error tells you about the history of the error. How has the error been big or small or positive or negative in the past? And then the derivative, you can think of that as telling you what is the error going to be in the next time instant, because we're looking at the slope of the error curve. So your controller is free to weight those three things, past, present, and future, arbitrarily, right? So in theory, you have 3 degrees of freedom, k prop, k int, and k dir, that tell you how much you're going to weight all three of those branches. And that's nice. 3 degrees of freedom, you get lots of variability. It makes the PID controller quite versatile because you're not locked into a single degree of freedom. On the flip side, it also makes it really tricky to tune accurately, because you can imagine that you might get 1 or 2 of the gains set, and then the third one you have to go all over the place. But then when you get the third gain set, you have to go back and fiddle with the first one. So that's why we have these different heuristic methods for tuning a PID controller. And we're going to go through one called the Ziegler-Nichols tuning heuristic. And just a quick note, it's my experience that not all students in 302 have seen this word before. So a heuristic, I guess if you're from the East Coast, heuristic, that's how they pronounce it back east, is, well, actually, does anyone have a good explanation for what a heuristic is? So a heuristic algorithm, in my book, is basically a set of rules that will produce a good outcome, but there's no proof as to why these set of rules make a good outcome. Okay, so you can think of it as experience has taught us these things, and they tend to work pretty well, and so they get codified in what's called a heuristic. This is different than, say, an optimal algorithm, which is then something that if you follow this recipe, you are guaranteed to get optimal results, or within an epsilon of optimal results. Sometimes a heuristic is all you can do. And so if the idea is you want to have a set of instructions to tune a PID controller from an arbitrary plant? That's a really hard task, right? If I was to ask you to sit down and tell me how to configure the P, the I, and the D, and I'm not going to tell you what the plant looks like, that's impossible. Like how could you ever hope to do that? So the idea here is that Ziegler-Nichols came up with some general guidelines without knowing anything about the plant. So this is a black box to Ziegler-Nichols. We still have access to it, so we can still test things. We can see its input and its output. But technically speaking, Ziegler-Nichols doesn't need a mathematical model of the plant to work. Okay, so enough teasing. We can get into what's called a modified Ziegler-Nichols. So the Ziegler-Nichols original is a little bit different than this, but this is one modification for if you don't even know if your plant is stable or not. Okay. So the idea here, and I will run through an example of all this as well using MATLAB. So, but I just want to describe what's going on first. The idea is you're going to limit yourself to initially just 1 degree of freedom. That is, we're only going to vary the proportional gain. And so the hope is that you can do it first until you stabilize the system. And then once you've stabilized the system, you're going to vary the proportional gain until you get what's called quarter amplitude decay to a step response. So these things are phrased significantly less mathematically than what we've seen before. And that's because one of the selling points of a PID tuning heuristic is that it ought to be implementable by technicians or people working with hardware who don't have this training in Laplace transforms or S-plane design, right? This is a phrase that once you see what the picture looks like, you don't have to know anything about damping ratios or overshoot percentages. So quarter amplitude decay simply means that the amplitude of the first peak relative to steady state, so we'll call that amplitude 1, and we'll call this amplitude 2. All this means, quarter amplitude decay, is that amplitude 1 is about 4 times amplitude 2. Okay. Right, so you could show this picture to anyone and say, when the step response looks like this picture, that's good. Oh, okay, the second amplitude is a quarter the height of the first amplitude. How are the amplitudes measured? They're not measured with respect to 0, they're measured with respect to the final value of the response. Okay. So why quarter amplitude decay, you might be asking? Well, this is one of the insights that Ziegler-Nichols had, is that if you can get, using just proportional control, the response to look like this, that actually isn't a good response. It's not, you shouldn't stop there. But what it does do is it sets you up well for the next 2 steps. Okay? So the idea is that we're just trying to get in the right ballpark in step 1. There's nothing to say that quarter amplitude decay is a good response. In fact, this is often way too large in terms of absolute overshoot. But the idea is that we're just trying to get in the right ballpark at first. Because then you're going to hold the K-prop that you just found steady, and then you're going to adjust the integral gain until the steady state requirements are met. This means, remember, by adding in the integral gain, we are essentially increasing the type number of the system. So technically, K-int equals 0.00000001 should increase the type number from whatever it was to that plus 1. But steady state means different things to different people, right? So if your integral gain is 10 to the minus 10, then yes, you will eventually act like a type 1 or above system. But that could mean you have to wait 10 years before you reach steady state error of 0, or of approximately 0. So the larger you make K-int, so when this thing gets bigger, the error in steady state goes to 0 faster. Right, and the idea is that you're adding more weight to the integral of the error, and so the error history counts for more, and so we're trying to correct that faster. This does not come without consequences, because as we mentioned in this slide, the higher your integral gain becomes, the larger your integrator wind-up overshoot becomes. And so the idea is you only want to do want as much as needed. Something's going on with my pen here. Because if you just keep pouring more and more k-int into the system, if you keep just ramping this number up, saying, oh, look, I can get my error to go to 0 super lickety-split, you're going to end up with enormous overshoots. Okay, so the idea is really only add as much of this as absolutely necessary, because any additional k-int that you add is only going to hurt you in terms of transient response. Speaking of transient response, let's talk about step 3. So once you've got k-prop in the right ballpark and k-int in the right ballpark, now it's time to bring in the derivative gain, because the derivative gain should help you meet those transient requirements. Right? We said how the derivative tends to counteract the integral in the transient regime, and that's how you're going to try and tamp this down, is with the derivative gain. Remember, the derivative part of the PID controller goes to 0 in steady state, so it's not like introducing derivative gain cancels out the integral gain over all time. It just tends to fight the negative aspects of the integral gain over the transient region. You will sometimes, once you do step 3, sometimes you're good to go. Sometimes you've got a stable system, you've got steady state error taken care of, and then you've got the transients met, you're good to go. Sometimes you don't need to do step 4. Other times, the steps 1 through 3 will get you in the right area, but then you'll have to go back. No, I don't want to draw it like that. Sometimes you'll have to go back. So how do I visualize this? I visualize this as kind of a 3-dimensional space. K-prop, K-int, and K-d. So what I view this as being like, steps 1 through 3 will get you somewhere in this space. And what I view step 4 as is kind of like making small excursions in this neighborhood to try and truly optimize the system. Now, the idea is that Ziegler-Nichols gets you in this ballpark, and then it's your job to explore around that ballpark to make sure that you can get things as good as you can do. The advantage of doing Ziegler-Nichols is this search space, this region, is way smaller than the region we started with, because the region we started with was the entirety of 3 space. Yeah, okay, so maybe you only want to do positive gains. That's a reasonable thing to say. But still, this little bubble is so much smaller than this positive orthant. Okay, so even if you don't buy the fact that this is a heuristic, it does serve a purpose in that it gets you a nice starting point to maybe a search algorithm. Okay, that was a lot of talk and not a lot of do. So I'll pause there for questions, but I want to bring in MATLAB and I want to show you this thing in action.
I think a lot more questions will come once you show us on MATLAB.
Okay, yeah, I understand. Okay, so here we are. I have got this system set up in Simulink. The plant, I believe, is defined here. Yeah, so the plant is second order, it's underdamped, and currently I am set up to do step 1 of Ziegler-Nichols. I've got k prop set to some arbitrary starting point, and k int and k dir are both set to 0. So I'll go back to Simulink so you can see what's going on. I am going to test this with a step input. And for starters, let's see. For starters, we are not doing anything with the integral gain because we're setting it to 0, and we're not doing anything with the derivative gain because we're setting it to 0. So this is, as I mentioned, a PID controller is a P controller as long as you set the others to 0. So the first step in Ziegler-Nichols is to adjust the proportional gain until you A, stabilize the system. The plant was already stable, so we've already got that under control, so to speak. And so then we're going to look for quarter amplitude decay here. So let's go back to MATLAB. And yeah, so if you want, we can talk about these things, but these are mostly just parameters for the Simulink modeling or the numerical solver. Where I'd like you to focus is this section here. And this section is simply to run the simulation and plot the results. So I'm just going to run this. Wait for it. There we go. Okay, so what are we looking at here? We have the input signal in blue. We have the output signal in orange. And we have the error in yellow. The integral of the error, what is it? You kids say these days, yeeting off this way. And the green signal is the derivative, so you get that delta function, or you get a numeric approximation of the delta function, which kind of goes off the screen here. And then the error is decreasing, so we get a negative slope here until it settles out to 0 in steady state. Again, we are not acting on green or purple because we've set those gains to 0. We are currently only acting on yellow. And so I don't think we have quarter amplitude decay here, right? I can't even hardly see the second peak of the output. We've got steady state error, but again, we're not supposed to be worrying about that until we get to step 2. So I am going to go ahead and commence with my Ziegler-Nichols. And let's say we try and increase the proportional gain up to 5. So that would be, set that to 5, run the simulation. Now we're starting to get a second hump here. So let's see if we can turn the grid on. Yeah, that might help some things. So, and also we can try and zoom in because I think the derivative signal is actually stealing the show here. It's kind of making the scale hard to read. Although I need to know what the steady state value is. Okay, so let's see. Let's say the steady state value is something like that. Whoa. So what I'm looking at is this is about, what do you call that? About 0.1 of a difference because these grid lines are 0.1. So here's 0.1, 0.2, 0.3. I don't know if you can tell, but I didn't mean to do that. This is about quarter amplitude decay right here. In fact, this is close enough that I'm going to call it good. I meant to do a couple more iterations, but I guess it's just my lucky day. So questions on why this qualifies as quarter amplitude decay? I imagine that there are some questions now. I mean, we can fiddle with it a bit more if you're not convinced. So maybe we can set this up here to 7.
Was that the second hump that is going to be the guy that we're going to determine whether or not it's quarter amplitude decay?
So you need both the first and the second hump.
Okay.
Right, because you're trying to measure this. Try to get the laser pointer here. You're trying to measure this. Oops, that's not what I wanted. This height as about 4x this height.
Oh.
Yeah, that might work. Wait for it. Okay. Okay, here we go. So it looks like the steady state value of this curve is about a little under 0.9. So I'm calling this a little over a 0.1 of an amplitude. And then this goes from here, there's a 0.1, there's a 0.2, there's another 0.1. So this is a little bit more than quarter amplitude decay because this peak is now about 0.5 in height, and this peak is only about 0.1 in height relative to this imaginary steady state line that I'm looking at going through the 0.9 line. You follow that? So I think I'd like to set this K-prop back down to 5 and rerun the simulation from there. Again, quarter amplitude decay is not, in general, a good result. It is, however, a good indicator that we're in the right ballpark to move on to the next step. Okay, so the next step is add just as much integral gain as you need to satisfy your steady state error requirements. So let's say that our steady state error requirements are that after 9 seconds, we need these two curves to be indistinguishable. I think that that's a nice qualitative way to state that my steady state error needs to be small as time goes on, right? So I'm just going to translate that to be if orange and blue are coincident here after 9 seconds, then we'll call that good. So I just want to inch the integral gain up. So again, I'm just going from 0 to something small down here, and we'll see if that has any noticeable effect. It did tend to slope this orange curve up. So I can see that because the purple curve actually dipped down. So we'll do that again. Go up to 0.2 for integral gain, rerun. And so this gap between blue and orange, which again, that gap is the error, is shrinking. And I hope you can see that this right there is wider than here. And that means that the integral of the error is picking up less area than it used to going forward. This is still not enough to satisfy my requirement. So I'm going to go ahead and point that up to 0.5. Run that. Run that. Now they're all starting to get a little chummy in there. So let's go up to 0.75. Unfortunately, they're all kind of in here together, but I still see some daylight between blue and the other curves. So let's go up to 0.85. Still a little bit of daylight. Still a little bit. That is not what I wanted. How do decimals work? Okay, so now we're getting close. Let's call this 1.1, and I think I'm going to call that indistinguishable. Like you could zoom in here, you can keep zooming, and you would see that there is eventually some daylight between blue and orange. But guess what? Because it's a steady state limit, remember the final value theorem is talking about the limit as time goes to infinity? At any finite time, if you zoom in on the difference between output and input, you're going to see daylight because it's only true in the limit. So we will commonly say a steady state error of 0 is required, but you as an engineer should probably drill into that and say, what do you really mean? Like at what time and what quantity do you technically call 0? That's an important question to ask of the people paying you. Maybe phrase it in a little bit better way than I just did. Okay, so I think that we are ready to step into step 3, unless there are any questions on what I've just done. Okay, so step 3 is increase K-dir until the transient requirements are met. What are the transient requirements here? I don't know, maybe let's have the overshoot be under 10%. I think that's a reasonable thing to ask. Right now, the overshoot is sitting at probably close to 25%. So let's see how the derivative gain, so I'm going to go 0.5 as my initial go here, impacts the transient performance. It should not impact the steady state performance. So let's confirm that that's true. Run that. All right, so I still see not a whole lot of gap here, but I hope that you'll see that the overshoot was dramatically improved. So maybe we can zoom in here to just double check. Yeah, that's going to be close to a 10% overshoot right there. So let's double check. Wait for it. Man, if I did this again, I don't think I would get this lucky. So let's see if we can nudge this up a little bit higher, 0.6, just to get us significantly under the 1.1 level. Run that again, and yeah, now for sure we're going to be underneath it. Sorry, my MATLAB does not necessarily like the tablet that I'm running it on here. Okay, so this looks like about a 7% overshoot. And if we zoom back out, the steady state error might have increased a little bit. So maybe we could play a little game here by going back and forth between kint and kdir. But I think that we took a 3 degree of freedom controller, a PID controller, and with relative expediency, we're able to narrow it down into a nice ballpark, right? This is something that we could then perhaps automate from here on out. So maybe this would look something like you run kind of a for loop or something like that. So this is what I imagine happening. So this gives you a good starting point for your search algorithm. So your search algorithm could say, look in ranges of k prop centered at 5, maybe go up 20% or down 20%. And then simultaneously search values of kint centered at 1.1 and search values of kdir centered at 0.6. Right, so this is, I try to bring these kind of modern techniques into this class because I think that a lot of students are disillusioned when they learn that everything we learned in 302, I think it's really cool, but it's not super useful in modern day systems engineering, just because everything is digital, everything is nonlinear. So what I'd like to do is, whenever I can, tell you how to use the things we're learning in this class in a modern day context. And so in a modern day context, you would do this with a computer, you would do this with simulation. But the idea is that Ziegler-Nichols can actually get you a good starting point for that simulation. Right? If we hadn't done Ziegler-Nichols, then what would this search space have looked like? It would have been from 0, I don't know, to some huge number. It would have been from 0 to some maybe slightly less huge number, but still unknown. My point is that Ziegler-Nichols gave us a good starting point, or a supposedly decent starting point for the search algorithm. Yeah, you're still going to have to introduce some of your experience or gut instinct to tell you what should the start and end points here be. But at the very least, we're not going from 0 to infinity, right? We've got a starting point for all 3 of these dimensions. So again, this class is not about search algorithms. This class is not about numerical methods at all, really. But what I do like to introduce you to is that Ziegler-Nichols is not some archaic thing that you can forget as soon as you leave. It could be useful even in a modern day context. So questions on that? Okay, so if you wanted to, we have satisfied all of the make-believe requirements that I laid out. But maybe you also want to improve the rise time. So this rise time is actually kind of sluggish, right? This is about a half a second rise time. So I think if we keep increasing k-dir, that's actually not going to help, because we saw that increasing k-dir has the effect, oops, go back. Because we saw that increasing k derivative actually had the effect of squashing this peak. And the effect of squashing this peak is to extend the rise time, right? If we're not rising enough to overshoot very much, then we're not rising very quickly. That's how those two things normally go. And so if we kept increasing k-dir, we would probably suffer for rise time. But we could also try something else. We could try to now go back to the beginning and perhaps try to increase k-prop and see how that affects things. So this is going a little bit rogue, or you could say this is our step 4 in Ziegler-Nichols. So what we've done is we haven't really made the steady-state error performance suffer. We have paid a small price for overshoot, but we've really sucked in that rise time. And the cool thing about this is that k-prop will have a different effect in step 4 than it did in step 1. Because in step 1, k-prop was the only animal in the zoo. So k-prop was doing everything for us. But now, the weights are non-zero on the other branches, and so wiggling k-prop by a small amount actually has a significantly different effect than it did when the other weights were 0. So now we can go back and start talking about messing with k-prop and k-dir in tandem. And we can now start trading off. We can shorten the rise time and then squash the overshoot. Shorten the rise time and then squash the overshoot. So this is what hopefully your search algorithm would do for you. It could perhaps automate this process. Is that running? Let's see here. Run it again. Okay, not a whole lot of change. So let's say we go up to 1.1 here, just because I want to get that overshoot down. Okay, yeah, so we're starting to tamp down the overshoot again. But now our rise time is sitting here at about, I don't know, 1/3 of a second. So this is the power of PID. It's a blessing and a curse, right? You can do lots of things with it, but it can be, if you let it get to you, it can be frustrating because there's a lot of things that you can always go back and iterate through. Questions on this so far? Let me talk to you a little bit about this tau value. I haven't touched it at all, but I think that I would be remiss if I didn't. So you'll notice that the proportional branch is exactly how I drew it last time. It just takes the error, scales it by k-prop, and then adds it. The integral branch, same. It takes the integral of the error and scales it by k-int, and then adds it. And note that you could do these two operations in either order, right? You could scale and then integrate, or integrate and then scale. They're linear operators, so it doesn't matter. The derivative block, however, is different than how I drew it on Wednesday's lecture. Because on Wednesday's lecture, the only thing in the derivative block was the Laplace differentiator. What I've got here is not quite a differentiator, but I want you to see that if tau is very, very small, if this is, say, I don't know, 10 to the minus 8, then this s is multiplied by a small number, and so it looks like s over 1. Okay, so on its very, like before we talk about why I would include this, these dynamics in here, I just want you to say that if I let tau be small, then I can recover, ideally, a perfect integrator. Sorry, a perfect differentiator. Okay, and then we're scaling it by k-dir. So my question to you now is, what the hell? Why would I change the pure differentiator to look like this? Any ideas? Well, first off, what is this system? Like, so it's a Laplace block diagram, so we are free to consider them as being in cascade. So there's your differentiator block, and here is your tau s plus 1 block. So I actually haven't asked, but I'm hoping that you're comfortable with me calling this a differentiator. What is this block doing? What name would you give it? Would it help if I wrote it in Fourier form? So tau j omega plus 1.
The first order filter?
That's exactly right. First order filter, low pass or high pass?
It's too early. I got the filter though.
Okay, okay. Someone else has to pick up where Caesar left off.
Is it low pass?
Yeah, when omega gets big, this fraction gets small. Okay. Yeah, this is a low pass filter, first order. Okay. So why is it a good idea to include a low pass filter in cascade or in series with your differentiator? Well, let's first consider what would happen if we didn't have it. So let's erase it. And so now we've just got this differentiator sitting. Oops, come on. And if everything is nice and ideal, like it was in the simulation that I just showed you, there's no noise. And the effect of the low-pass filter is completely non-existent. In reality, there is always going to be some kind of noise, whether it's regular noise like we see in the MCSL, or it could be random noise, or it could be thermal noise, or it could be shot noise. There's all these different sources of noise, and what they all end up doing is they end up making some wiggles sit on the signal that you actually want to be feeding through your system. Okay, so this is a gross simplification of what's going on, but let's say that there are some oscillations that we didn't really want. They're small, but they're oscillations nonetheless. If I differentiate that signal, is the result going to be flat or oscillatory?
Oscillatory.
Good. Is the amplitude going to be bigger or smaller if these oscillations are quite frequent?
I'm gonna guess bigger.
All right, so it's early for everyone here. Right, so what happens if they were just pure cosines? If they were cos, I don't know, a kilohertz, 10 to the 3 times 2 pi times t. If I differentiate this signal, and it starts with amplitude 1, then the derivative has amplitude 10 to the 3 times 2 times pi. It's a sine, but nonetheless. So this is the oscillatory part that Billy got. This is the amplitude that I'm talking about. So, and the higher the frequency of these, the bigger the amplitude of these. Okay, so the differentiator is a good idea in theory, but it is a very difficult beast to implement in practice because of the presence of noise. Now, we haven't talked about noise really at all this quarter. It's not actually part of this curriculum, but it would be irresponsible of me to teach you about PID controllers and not teach you about filtering, like how you would actually use them in practice. So have I convinced you that this could be a problem? Like you don't have to know anything about statistics or white noise or anything. You don't have to know anything about any of that. If there's wiggles on the input of a differentiator and those wiggles are reasonably high frequency, the output wiggles will be large. Are you with me on that?
Yeah.
I said, are you with me? No, I'm just kidding. I know it's early. So this is, I hope you can see why one would add a low pass filter, is if you can introduce something that gets rid of the wiggles. So if we put a low pass filter here, then as long as this corner frequency allows the good part of the signal to pass and starts to try and block the high frequency wiggles here, we can get something, hopefully, that's no worse than what we started with, okay? So that's the idea of why you would want to add a low pass filter. The tau here controls the corner frequency. As the reciprocal, right? So tau is a time constant measured in seconds. So the reciprocal of tau gives you the corner frequency in radians per second. Smaller tau gives you a higher corner frequency. So tau small means omega corner big. And so this is why if you were to make this 10 to the minus 8 or whatever, that would essentially be saying, hey, all you high frequency noise components come on through. Right? I can handle noise up to 100 megahertz or whatever. So, and I mean, that's essentially what we're doing. We're setting this corner frequency to be very high frequency, which means it's not really doing much low pass filtering. So in practice, you don't want this tau to be, nanoseconds. You want this tau to be placed such that the dominant noise frequency that you see in your system is attenuated. So for example, in the lab, we get a lot of mains noise in our measurement signal. It's either 60 hertz or 120 hertz based on if it's full wave or half wave rectified mains. So we're going to have to end up designing a corner frequency here that will attenuate that, or at least not pass it or not amplify it, okay? When we start learning about frequency response, and this is looking far into the future, and by far I mean 1 week, we learn about frequency responses. If we plot on the frequency axis here, a differentiator has a slope like this. So this is the magnitude of a differentiator as a function of frequency in decibels. I guess I provided this the log scale. So this is a Bodie plot for a differentiator. If I were to cascade this differentiator with a low pass filter whose Bodie plot looks like this, then, and again, this is a jumping ahead a bit. If I add a slopey thing with a flat thing, I get a slopey thing until I get a slopey up here and a slopey down here, and I end up with a flat thing there. So this is the total Bodie plot of the combined S over tau S plus 1. Okay, so here, this is, again, relying on stuff that I haven't covered yet, but the low-pass filter, so here's your low-pass filter frequency response. It will stop the differentiator from doing its thing. So this is the differentiator thing. It just rises at 20 dBs per decade over all frequencies. Once I cascade it with the low-pass filter, it still does its differentiator thing at low frequencies. And that's a good thing, right? We want this differentiator to be active at low frequencies. That's kind of why we included it. We want it to help us with the transient response. You don't want to move the corner frequency too low, because then all of a sudden you only get a small fraction of your frequencies being differentiated. This is the balancing act that you have to make as an engineer. Is you need to attenuate noise, so you need the low-pass filter somewhere in here, but you also need the differentiator to help you with your transient metrics. So you can't, it's a bad idea to put your low-pass filter corner down there. Okay, so there has to be a sweet spot. And that sweet spot is well informed if you know the dominant frequency of the noise. Okay. We have a fraction of one lecture left, but not 4 minutes of one lecture left. So we will conclude Unit 6 on Monday, which means your Unit 6 homework will be due a week from Monday. I will post it this weekend in case you want to get started on it. Or if you want to take a break this weekend, I would understand if you want to do that. Okay. Questions? I guess we can wrap up with some questions.
So for the noise, oh shoot, my bad. Go ahead.
I think Ivan had some noise in the background there.
So for the noise when it comes to KDR, can we say that noise is coming in through all Ks, and how come we don't place a filter in all those as well?
Good question. So this was actually asked on Piazza last night as well. So the frequency response, and again, I know I'm getting into things that I haven't covered yet, but the frequency response of a gain, the frequency response, the Bodie plot of a gain term, so here's log omega, is flat. So this system is going to, if it sees noise at low frequency or if it sees noise at a high frequency, it's going to do the same thing. It's going to scale it by k-prop. This system, the integral system, has the opposite Bodie plot as a differentiator. It has this kind of slope. And so the integrator itself is the world's best low-pass filter, right? It definitely passes low frequencies. In fact, it blows them up, but it kills anything at high frequencies. So this is already, you can think of this as a low-pass filter. Now, if you really wanted to, you could additionally filter here. You could put a low-pass filter there. The problem with this, if you put your low-pass filter here instead of down in this branch, because there are advantages to doing this. If you put your low-pass filter here, then all of a sudden you can take care of high-frequency stuff that might have been scaled up by a proportional branch. The issue with putting the low-pass filter here and not here is that this signal will have already gotten large and may be saturating your op-amp or your intermediate signals here. Okay, so it's often nice to nip these things in the bud before they can be amplified. So in truth, this would, if you were constructing this would be a low-pass filter here and then the differentiator downstream of it, right? Instead of the other way around, because the differentiator, if it came first, quote unquote, first in the loop, it would amplify the noise up, which you would then have to filter down. And the going up first has the practical consideration of perhaps saturating your op-amp. So if you filter first, then you can make things small, and then perhaps your differentiator makes them big again, but it should only make them as big as they used to be. That's the same idea about this branch here. K-prop usually tends to be not terribly large, but importantly, it doesn't make things bigger at high frequencies than it does at low frequencies, i.e. it is constant overall frequencies. So I wouldn't blame you if you wanted to put a low-pass filter here and here, but if you only had time to put the low-pass filter in one place, it's got to be here.
Okay, that makes a lot of sense. Thank you.
Cool. You're welcome. Okay, people. Thank you very much, and I will see you in office hours.